Welcome to this WestGrid Summer School presentation on Gromacs simulation optimization. My name is Olivier. I work at the University of Saskatchewan and I have used Gromacs until very recently and for many years as a tool in my own research. In this session, I hope to teach you how to maximize the performance and the throughput of your MD simulations with Gromacs. I also want to teach you the basics of how Gromacs performs works in parallel. You will most benefit from this session if you are already reasonably familiar with MD simulations and Gromacs, but you do not already have a deep knowledge of Gromacs' parallel architecture. I intend to keep the topics mostly technical rather than scientific, but due to the nature of MD, it's not really possible to completely separate the two. In addition to this pre-recorded presentation, the slides are available online, and there will be an interactive Zoom session starting at 11 o'clock Vancouver time to allow you to ask your questions. There are several topics I would like to touch today. First, we'll start with our motivation. Why do we want longer trajectories and faster MD? Then I'll go back to the basics with some concepts in parallel computing. Then we'll see what is the deal with MD. Why is it seemingly so slow? And we'll see that non-bonded interactions are the cause. Once we have these basic concepts under our belt, we'll be able to jump into Gromacs parallelism. We'll see that there are three parallel strategies in Gromacs: domain decomposition, shared memory parallelism, and hardware acceleration. Once we've understood that, we'll be able to go to this would ideally be an interactive tutorial on how do we optimize the simulation in practice. Since it won't be an interactive thing today. Instead, I'm going to show you a set of guidelines that you can follow to optimize a simulation. Then we'll add another layer of complexity on top by using Gromacs with GPUs. Then we'll look at how non-bonded interactions should be tuned in order to have optimal performance. And I will conclude with a few tricks, either integrator related or on some other topics. Then I will give you pointers to documentation, and finally I have included as an annex an example MDP file for recent version of Gromacs that allows you to have an optimized parameter set. Let's start with our motivation. Why do we care so much about the performance of MD simulations? And the answer is actually pretty easy. More simulation time means better sampling of biological events. If we have a look at this figure, this time scale of biological events, we can see that in a typical molecular system, we have very fast events happening on the femtosecond to picosecond timescales, such as bond vibrations. Then if we want to see some slightly more interesting things, side chain rotations, for instance, we are already down to the nanosecond timescale. But if we want to see really relevant biological events, such as ligand binding and catalysis in an enzyme, we need to break the microsecond barrier. And the most interesting events actually happen on the millisecond timescales. Protein folding unfolding can even be slower than that. If we compare here on the bottom to when these timescales became accessible to MD, we see that we still have a long way to go. The first MD simulation that was published in 1977 was only on a few tens of picoseconds. And it took nearly 20 years for us to reach a single nanosecond, going from one small protein in vacuum to another very small protein, this time in explicit solvent. And it took until 2008 until we could actually break the microsecond barrier. In 2010, one research group was able to present a trajectory of a full millisecond using specialized hardware that has been custom built for MD simulations. So this is not a computer that is accessible to most scientists, and it's a computer that only works for rather small systems. So as we can see, we still have a lot of work to do in order to get trajectories that are relevant from a biological point of view. So we really want to squeeze all the performance that we can from Gromacs. So how do we make Gromacs faster? Well, the only way we can do that is really using several CPUs in parallel. I cannot simply give you a more powerful computer. So instead we use several computers at once, or we use GPUs as accelerators. But when using CPUs in parallel, there is always a loss of efficiency. What I mean is that if you double the number of CPUs to perform your simulation, you won't always double your performance. Which raises a few questions. First, how do we measure this efficiency? Second, why does this efficiency decrease when we increase the number of CPUs? And of course, how can we avoid or at least limit this loss of efficiency? And the last question is, how does that translate into simulation parameters? How do we configure our simulations to take advantage of multiple CPUs and be as fast as possible? Let's start by going back to some basic parallel computing concepts. First, Speedup, which is the ratio of the time it takes to execute a program in a serial manner over the time it takes to execute the same program in a parallel environment. For example, if you have a program that takes 10 minutes to complete on a single CPU core, but it takes only 6 minutes to complete when you run it on 2 cores, then you have a speedup of 10/6 or 1.67. Then we have the efficiency, which is the ratio of the speedup over the number of parallel tasks. If we continue with our previous example, the 1.67 speedup, if it's associated with 2 cores, means that you have an efficiency of 0.835, which we usually report as a percentage. And this gives you a good idea of how efficiently you are using your computational resources. Here we can say we are using about 84% of the computing time that we were allocated. And when the speedup is equal to the number of parallel tasks, that means that the efficiency is 1.0. We say that the efficiency is linear, and this is really the ideal case. Now, how well does Gromacs scale? The Gromacs developers gave us a rule of the thumb. They said that the scaling limit for Gromacs is around 100 atoms per CPU core. What this means is that at that point, if you add more CPUs, you won't make your simulation go any faster. However, the decrease in efficiency starts long before that. If we have a look at the figure on the right, here I'm showing the scaling of Gromacs on a supercomputer in Germany for a 150,000 atom system. We have on the y-axis the performance in nanoseconds per day as a function of the number of cores on the x-axis. And we have a black line that delineates linear scaling. So if we follow this black line, we have an efficiency that's very high, near 1.0, but when we stray away from it, our efficiency decreases. What we can see is that for a lower amount of cores, we are very efficient, up to say 128. When I double again the number of cores to 256, I'm still pretty near to linear scaling. If I double again to 512, however, my efficiency decreases significantly. And at that point, if we take the ratio of the number of atoms and the number of cores, we can see that I have about 300 atoms per core. So if I were to double this again and use 1,000 cores for the simulation, my efficiency would go very low because I would be pretty close to the scaling limit at around 150 atoms per core. The efficiency of your simulation is going to depend a lot on system size, but it's also going to be a factor of the composition and your simulation parameters. Therefore, it is pretty difficult to predict the efficiency, and to avoid wasting resources, you should really measure your scaling and re-optimize every time you have a new molecular system or a new parameter set. Why is it so difficult to make MD simulations fast? Well, you already know that MD simulations are about solving the equations of motion. We want to integrate the forces and move the atoms around, and we do this by computing interatomic potentials based on the force field. Here on the right, I have a typical force field with bonded terms on the top and non-bonded terms on the bottom. Interestingly, the non-bonded terms take a lot of time to compute compared to the bonded terms. Why is that? If we consider an example, say we already have a 1000 atom system, and we say, I want to add one more atom to that system. Well, maybe that atom will be bonded to one or two other atoms, maybe to none, perhaps to 3 at the maximum. So you will be adding 0 to 3 new bonds, a few angles and dihedrals that go with them, but that's it. However, when you add this atom to the system, for the non-bonded interactions, you add 1000 new non-bonded pairs, because the atom could be interacting with any of the other 1000 atoms in the system. This means that for non-bonded interactions, the complexity grows quadratically with the number of atoms, or with n to the square. And clearly, this is not sustainable. To solve this issue, we only compute the non-bonded interactions between atoms that are close in space. We define a cutoff, for instance, say 10 angstrom, and atoms that are farther apart, we don't even compute the potentials, the non-bonded potentials between them. This means that we forego long-range electrostatics, which is a problem. We know long-range electrostatics are important. Therefore, we add them back to the equation by using what we call the particle mesh Ewald method. Internally, Gromacs uses what we call neighbor lists to keep track of the atoms that are in proximity. These lists are updated as the simulation progresses. And Gromacs uses what we call verlet lists. So if you ever see that name in the documentation, you will know what it's about. Thanks to neighbor lists, the complexity goes from quadratic to a function of n log n, where n is the number of atoms in the system. With these introductory remarks out of the way, it's time to jump into the really interesting stuff, which is how does Gromacs perform parallel work? Actually, Gromacs uses an hybrid approach to parallel programming with 3 different levels of parallelism. What is very interesting is that all these levels are independent, but they also can be used together. This makes Gromacs very flexible. It's able to take full advantage of modern supercomputers, but it will also run very well on a laptop and in fact on a variety of different computing environments. However, there is a downside to this complexity, and it's that if you want to take full advantage of Gromacs, you, the user, need to understand how the program works and to pay attention. Here on the right, I have the 3 different levels of parallelism in Gromacs: the spatial domain decomposition at the top, then shared memory parallelism, and then hardware acceleration using SIMD instructions and GPU computing. It's not important at this point to really understand how these levels work together. As I said, they can all be used independently. So instead, we'll look at them one by one, and once we understand them, we'll go back to this overview and put the pieces together. Let's start with the first level of parallel work, spatial domain decomposition. And imagine that we have a simple system, a water box, to perform MD on. If we perform MD using a single CPU core, then obviously that core is responsible for everything. It needs to compute all the non-bonded interactions, both the short-range interactions, using cutoffs and neighbor lists like we've just shown, and the core also needs to compute the long-range interactions using the particle mesh Ewald technique. With spatial domain decomposition instead, we break up the system into smaller cells. For instance, here on the right, I've shown our water box being split into 12 different cells. And one CPU core will be responsible for each of these little cells. In addition, the long-range electrostatics will be under the responsibility of different CPU cores. So here, for instance, I would have 14 CPU cores working together on the simulation. 12 of them would be working on what we call the particle-particle part of the systems, and 2 of them would be working on the PME, particle mesh Ewald. So Gromacs performs this domain decomposition using MPI, the parallel library, and some MPI ranks will therefore compute the short-range particle-particle potentials, we say the PP ranks, and other MPI ranks will be responsible for PME, we call them the PME ranks. Here I show domain decomposition in 2D but it's possible to do it in 3D. That's usually what happens actually. Now, if we consider a specific cell, a specific particle rank here inside the system, we can say, well, the CPU core that's working there is responsible for the atoms inside that little box and not for the other atoms in the system. However, it will need to exchange information with the CPU cores that take care of the neighboring cells, because the atoms here are pretty close to those there, so there will be non-bonded interactions between them. However, this particle rank will never need to communicate with the cells that are far away because the atoms are too far. They're not going to interact. So because of this, communication is minimized. Each CPU core only needs to communicate with the minimal amount of other CPU cores in order to perform the work. And Gromacs does all of this automatically. It optimizes the way the cells are organized and how the ranks are split between particle, and PME automatically. So spatial domain decomposition has many advantages. First, it can be distributed on many compute nodes. And that's actually the only way you can run a Gromacs simulation on many nodes. So this really allows you to take the scaling to a very large number of cores. Also, spatial DD works very well for large systems. If you can maintain more than 1,000 atoms per domain, so per cell, you have effectively 1,000 atoms per CPU core, and that's very efficient. Also, because the system is split in small cells, and these cells only need to take care of a fraction of the atoms in the system, this minimizes the necessary amount for each CPU core. And that means you can make better use of the CPU cache and things are going faster. However, DD also has some disadvantages. First, it has a significant overhead. You always need to communicate positions between the domains, and sometimes this is just not worth it for single node simulations. If you need many nodes, you have to use MPI and domain decomposition, but if you're doing a simulation on a single node, sometimes that's not worth it. Also, spatial domain decomposition performs poorly for systems that are already small because there is a limit to how small the domain decomposition cells can be. Another thing to say is that spatial domain decomposition requires a fast network interconnect. I list this as a disadvantage, but it's mostly just a way MD simulations are. MD simulations are by definition a very fine-grained parallel problem. So in order to make an MD simulation on several nodes, you will need a fast interconnect, such as InfiniBand or OmniPath. If you have only Ethernet, this is too slow. Fortunately, the Compute Canada clusters all have fast interconnects, but this is something you should be aware of if you are running Gromacs somewhere else. Now let's have a look at how this is done in practice. This is a typical submit script for Slurm that you would use to run Gromacs in parallel using MPI and domain decomposition. So let's go over this. First, we say that this is a bash script. We say this is going to be run on, say, a single node, and we're going to request 32 CPU cores on that node. So this means, for instance, if you have nodes that have 32 CPU cores, you're using the full node. Then we load Gromacs, we load the compiler, the MPI library, and Gromacs itself. And then we wrap all this in srun. We call srun with Gromacs, the MPI version of Gromacs, and we call mdraun. So this is enough to get us started on an MPI simulation with Gromacs. Now here's a slightly different example. If I want to run the same simulation, still using full nodes, but this time I say I want to use 2 nodes at the same time, I just have to change the nodes parameter here to use 2 of them, still using all the cores on each node, and that's it. Sometimes your system will be too small to work well on a full node, so it is possible to use only a fraction of the node. For instance, here, by lowering the number of tasks per node, You can say use only 8 CPU cores on a single node. What, however, you must never do is to use only a fraction of the nodes on one core, a fraction of the cores on one node, but to use multiple nodes. This here, for instance, says use 2 nodes and 16 cores, but put 8 of them on one node and put the 8 others on a different node. This means that there will be more communication via the network, and this is very bad for Gromacs. So never do this. Another problem that happens often is to specify the number of CPU cores that you want to use, but just using mtask, which essentially tells Learn, I want 32 CPU cores, but I don't really care where they are. They could be on one node or they could be spread on many nodes. This is very bad for Gromacs. Since Gromacs is very fine-grained parallel program, all the tasks need to be close together. If possible, they need to be on a single node, and if you're using multiple nodes, you need to fill the nodes entirely. So never do this either. Now, once you've performed your simulation, there are also interesting things you should see in your MD log file when using MPI. First, if MPI is enabled in Gromacs, you will see it. It will show MPI library. Then there will be a summary of the hardware you are running the simulation on. For instance, here you can say, okay, you had 2 nodes with a total of 80 cores, blah, 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 40 cores on each node. Then, if you're using MPI with domain decomposition, Gromacs will report how it actually performed the domain decomposition. It will say there were 80 MPI ranks. I used some of them for particle-particle work and others for particle mesh eval, here 6460. And this is Gromacs' best guess as to what is optimal. Then you will see this report that it started the simulation using 80 MPI processes. Sometimes you will also see warnings in the log file, for instance saying, oh, you lost quite a bit of CPU time, your efficiency is pretty low. And often this will come together with there was a bit of performance that was lost because there was an imbalance between the PME ranks and the particle-particle ranks. When that happens, Gromacs will also give you suggestions as to how to solve these issues in the log file. However, in my experience, I have to say that usually these suggestions, well, Gromacs already did the right thing. You can try to activate, say, dynamic load balancing or tune the number of PME ranks manually, but you are unlikely to get better performance. When this happens, in my experience, is because you've reached the scaling limit using only MPI. So maybe you should use fewer MPI ranks, or maybe you should try using OpenMP and shared memory parallelism instead. And this is exactly what we'll be considering now. The second level of parallelism in Gromacs is the shared memory multiprocessing. This is a lot simpler than spatial domain decomposition. Instead of splitting the system into several cells and giving each cell to a different CPU core, we simply say all the CPU cores have access to all the atomic positions and they work together to to compute the interatomic potentials. So if you have 1000 interatomic potentials to compute, they will be split between these, say, 8 cores that work. So each core will end up working on about 100 or so interactions. This is simpler and it's implemented by Gromacs using OpenMP threads. OpenMP threads, they can compute the particle-particle interactions, but they can also compute the particle mesh eval, and they can do both. Now, this is very different from MPI and domain decomposition, and it has advantages and disadvantages compared to it. Well, first, the computational overhead is pretty small. You're not splitting the system, you're not doing anything very complicated. And it usually works well on a single node. In fact, it performs better than MPI domain decomposition for small systems. Say you have less than 1000 atoms per core, usually OpenMP will be better. However, it also has disadvantages. It uses more memory per core compared to MPI, so the CPU cache is used less efficiently. More importantly, it's not possible to distribute the workload over several compute nodes using OpenMP. This can only be done with MPI. However, remember that I said the different levels of parallelism in Gromacs can be used together. This is the case here. We can use MPI and OpenMP together across many nodes, so that's possible. However, let's start by looking at an example of how we can use OpenMP and shared memory multiprocessing in Gromacs. This is another job submission script for Slurm, this time not using MPI but rather OpenMP. So we start in the same manner, we say this is a bash script, and this time, however, our options are very different. We start a single task, and task 1, and we say we want to have several CPU cores for this specific task. So CPUs per task, 32 here, which means we'll be using one full 32 core node, for instance, on Cedar or another cluster. Then we load Gromacs again, and we will again run Gromacs using srun, but this time it's going to be slightly different. We're not calling the GMX MPI, we're calling the standard GMX, which is compiled only with OpenMP, not with MPI. Before that, however, we need to tell the environment how many OpenMP threads to use, which is done by setting the OMP numthreads variable, and we set it to the number of CPUs that we requested from Slurm. So export OpenMP numthreads equals Slurm CPUs per task, which will be replaced by this value of 32. Sometimes you will not want to use a full node with OpenMP if you're working, for instance, on a very small system that does not scale well to a full node. This is possible. We can simply reduce the number of CPUs per task. Say here I want to use only 1/4 of a node, CPUs per task equal 8. Your log file will also contain some interesting things if you use OpenMP. First, OpenMP support will be reported, OpenMP support enabled here. Then it will tell you again what is the hardware it's running on, one node, 40 cores, blah, blah, blah. And then it will tell you, I started the simulation using 40 MPI threads. Using 40 OpenMP threads. I mentioned previously that the different levels of parallelism in Gromacs can be used in combination. It is possible to use domain decomposition and shared memory multiprocessing together. In that case, if we go back to our overview figure of parallelism in Gromacs, we can see that OpenMP is on the first level, MPI is on the first level and OpenMP on the second. This means that MPI ranks actually control OpenMP threads. Each MPI rank will control the same number of OpenMP threads. This has both advantages and disadvantages. First, you can use more CPU cores in parallel without having to perform more domain decomposition, which is great because sometimes it provides you with just this little added performance increase. Because you cannot perform domain decomposition indefinitely, but here instead, you can still add more cores without having to perform more domain decomposition. However, there are disadvantages. First, it's more complex to set up. You need to fine-tune also the number of threads per MPI rank. And of course, it has the overhead of both methods. You have both the overhead of using MPI and the overhead of using NP. So sometimes it's not as fast as using only pure MPI or pure OpenMP. Here is an example Slurm submit script, this time using both domain decomposition and shared memory. We're still trying to use a 32-core node. We want to use it fully, but this time we want both MPI ranks and OpenMP threads. And we say each MPI rank controls the same number of OpenMP threads, so we'll go with 16 MPI ranks, each controlling 2 threads, for a total of 32. This translates to the following options. We request one node, 16 tasks per node. Tasks per node will become the number of MPI ranks or MPI processes. And then we say CPUs per task equals 2, which means we request 2 threads per process, so 2 OpenMP threads. Then we load our Gromacs module as usual. We set the number of OpenMP threads, as we did before, from the number of CPUs per task that we requested via slurm. And we start Gromacs wrapped in an srun call. Since we are using both MPI and OpenMP, it is possible to split the job over several nodes. Here, for instance, we increase the number of nodes to 2, and we keep all the other parameters identical. We still have 16 tasks per node and 2 CPUs per task. So this means we'll be using 2 full 32-core nodes, and we'll still have 2 OpenMP threads per MPI rank. What you should not do, however, is to say, oh, I'm going to request several nodes, but I'm going to have one single MPI process on each node, and that process will take care of OpenMP threads for everything. There will be 32 OpenMP threads doing all the work, controlled by a single MPI rank on the node. It looks like it should work, but it actually doesn't. The reason is purely technical. With Gromacs and domain decomposition, the optimal number of threads per rank will usually be somewhere between 2 and 6. In my experience, it's usually 2. Going to 3 or 4 threads may work on some very specific hardware, but usually it's either pure OpenMPI or OpenMPI plus OpenMP with 2 threads per process when working with hybrid parallelism and you want to use several nodes at the same time. Now let's have a look at our log file for such a hybrid MPI OpenMP. First, we'll see both support for the MPI library and OpenMP. We'll see the summary of the hardware we are running on. We'll see the remarks about the number of OpenMP threads. And we'll also see the domain decomposition. So we have both. And when the simulation is started, Gromacs will report that it's using 80 MPI processes. Here we have 40 MPI processes on each core and using 2 OpenMP threads per MPI process. You may encounter the same problems as you have with pure MPI, which is that the balance between particle-particle and particle mesh evolve is not working properly. When that is the case, you can again try to optimize this via dynamic load balancing, but in my experience, you've just reached the scaling limit, and at this point, you should just stop. You've optimized your simulation correctly. There actually was a small typo in the slide here. This should have read using 40 MPI processes and using 2 OpenMP threads per MPI process. We are now ready to tackle the third and last level of parallelism in Gromacs, which is hardware-based acceleration. You might know that modern CPUs are able to apply a given operation or sequence of operations to multiple data points at the same time. This is what we call single instruction multiple data, or SIMD. For instance, the Intel CPUs support AVX, AVX, and AVX512 instruction sets that allow programmers to achieve this hardware-level parallelism. And Gromacs has been coded to take advantage of these specialized instruction sets in order to be faster. The routines for hardware acceleration in Gromacs must be chosen at compilation time. On the Compute Canada clusters, this has already been done for you. Gromacs is optimized, and we did that carefully. So there is nothing special for you to do at runtime. However, you can still check in your log file that the correct acceleration routines have been selected. For instance, here at the start of the log file, I will see which SIMD instructions Gromacs was compiled for. Here, AVX512. And there, I can see later in the log file the hardware detection on the node saying, yes, you do have our AVX512 units, so you have the correct SIMD instruction set. If you ever see this message here in red, then there's a problem. Here, for instance, I can see highest SIMD level requested by the nodes, that was AVX512. But then it says the SIMD instructions that were selected at Gromacs compile time were AVX2. So there is a mismatch. When that happens, you need to either recompile Gromacs yourself or ask the support on the machine you are working on to help you with this. Now, I said that Gromacs on the Compute Canada systems has been optimized already. However, there is a caveat. On Beluga, all the compute nodes support AVX512, which is the most recent version of the AVX instruction set. For that reason, the default software stack on Beluga was built for AVX512. On Cedar and Graham, all the compute nodes support AVX2, however, and some nodes also support AVX512. For that reason, the default software stack was built for AVX2. It is the smallest common denominator. However, it is possible to manually load the AVX512 software stack if you use the AVX512 capable nodes. I ran some tests with Gromacs on the Skylake and Cascade Lake nodes, those that are AVX512 capable, and saw a 20 to 30% performance increase when using the proper AVX512 software stack. However, you need to balance this with the fact that if you limit yourself to Skylake and Cascade Lake nodes, you will wait a lot longer in the queue. So it depends on the allocation you have on the machine, and you should test on your own system to see if it makes a big difference or perhaps not. Now, if you do want to request these spatial nodes, here is how you can do it. We take the example for MPI that we had previously, but this time we add another instruction in SBatch. We say constraint, either a Skylake or Cascade Lake node. And before loading Gromacs, we load this spatial architecture module, which says load the software stack for the AVX512 capable nodes. Now that we have covered all three levels of parallelism in Gromacs, it's time to discuss how we can optimize a simulation in practice. The trick is to make short tests. 10 picoseconds would be enough, or adjust the number of steps in order to get, say, at least 5 minutes of runtime. You don't want to have less than that because you need to give some time to the compute nodes to stabilize and get a statistically relevant sampling of how fast Gromacs is. While you perform your test, you should always deactivate the output to avoid input-output problems. For instance, if the file system was slow, this could actually slow down Gromacs and could end up skewing your results. You don't want that. You're not interested in the output files, you just want the speed of the simulation. So you can set the output trajectory, log file, and energy calculation to it never happens. The Gromacs performance will always be at the end of the log file, expressed in nanoseconds of simulation per day of computation. You should repeat those tests at least 3 times and use the average performance. If you run only one test, you might be unlucky and get on a node that was faulty, or you might be victim of a network problem or something like that. So it's important to repeat tests 3 times and verify that there's not a big deviation between the runs. If there is, you might suspect that something is wrong on the hardware or with the network or anything really. To optimize, always start with a serial run, that is to say, running on a single CPU core with nodes equal 1 and tasks per node equal 1. Then try increasing the number of cores progressively until you occupy all the cores on the node. This will be done using the MPI implementation of Gromacs, so you increase n tasks per node to 4, 8, 16 until you reach 32, or whatever is the number of nodes, of cores on the node you're working with. Then compute the speedup for each of these configurations, and then compute the efficiency for each configuration. You will see if the efficiency is still acceptable once you've reached a full node. Maybe yes, maybe you're still pretty linear, maybe not, maybe you've already reached the scaling limit. If you think it's still possible to increase performance, now that you're occupying a full node, try to use more nodes. So increase the number of nodes progressively, again by powers of 2, until the efficiency becomes unbearably low. So again, using the MPI implementation, increase the number of nodes, and always use full nodes. Once you've chosen an optimal number of nodes, because you know that if you ask for more, you will get rather bad performance, you can try fine-tuning the number of OpenMP threads versus the number of MPI ranks. For instance, if you said, oh, my simulations run best when I use 4 complete nodes, then you would request 4 nodes, but you could test, let's see, if I decrease from 32 to 16 MPI processes, but I use 2 OpenMP per process, what's the difference? There might be a small or a significant difference, and once you've performed this OpenMP tuning, you will have pretty much finished your optimization. On the other hand, if the efficiency was not acceptable at all on a full node, what you should do instead is repeat your test using only OpenMP instead of MPI. Because if you cannot use several nodes, usually it's better to just switch to OpenMP since the overhead of OpenMP is lower than the overhead of MPI. However, you still need to test it. It may not be the case for your particular system. GPU computing has become very popular, and Gromacs is able to use GPUs to accelerate the computation of short-range non-bonded interactions in a way that's a bit similar to SIMD on CPUs. However, GPUs are a lot more massively parallel than SIMD instruction sets. So they are very well suited to MD simulations, and they can be much faster than CPUs for certain tasks, especially single-node jobs. However, when people think about GPU computing, they often think, oh, maybe I can get a 10-fold better performance or something. This is often the case if you have a poorly optimized program for your CPU and then you move it to the GPU. Gromacs, however, already has excellent CPU performance and was fine-tuned to use CPUs as best as possible. Therefore, using GPUs will not make such a big difference. You may, in the best of cases, be, say, twice faster, but you won't be 10 times faster. Also, using GPUs works fine when you use a single GPU, but using multiple GPUs, especially on several nodes, is often not much faster than using only CPUs. What is undeniable, however, is that GPUs offer a massively increased throughput, that is to say, the total amount of simulation time that you can perform. So if you're not interested in having one single simulation running as fast as possible, but you say instead, oh, I could have 10 simulations running in parallel, GPUs are definitely the way to go. They will give you maximum throughput. The way Gromacs works with GPU is that one MPI rank is tied to one GPU. That means there should always be as many MPI ranks as there are GPUs that you want to use. That, however, doesn't preclude the use of OpenMP. Each MPI rank can still use OpenMP threads so that you can use all the cores on the node and also all the GPUs. Here's an example showing how to run a Gromacs simulation with a single GPU. So we'll be using the OpenMP version of Gromacs plus GPU, not the MPI enabled version, because we don't need it here. Since we're only using a single rank, we don't need more than that. Since we're only using one GPU and the GPU nodes on Cedar have 4 GPUs, we won't be using all the cores. We'll be using 1/4 of the core since we use 1/4 of the GPUs present on the node. So we specify that we want 8 cores as CPUs per task, and we say we want 1 GPU. This is done using the gres option. We say 1 GPU. This is the type of GPU you want. You will need to check this on the Cedar or Graham or Beluga technical specification, and then the number of GPUs you want. Our module load instructions here are a bit different. We also load CUDA, which is the NVIDIA implementation for GPU computing. Then we set the number of open empty threads and we start Gromacs. If we wanted to use more GPUs, for instance, all the 4 GPUs on a node, we can do it, but then we need 4 MPI ranks. So now we need to use the MPI-enabled version of Gromacs. We need to specify the number of tasks, which is going to be equal to the number of GPUs. This is also the number of MPI processors. So I want to use 4 GPUs. I put in 4 MPI ranks. I still keep the number of cores to 8 per task, so that I will be occupying 4 times 8, 32 cores, the full node. Then the module load instructions are identical, and I run Gromacs MPI again. You could even run MPI on several nodes and take advantage of the GPUs on all the nodes. For instance, if you wanted to use 8 GPUs on 2 nodes, you could do it this way. Increase the number of nodes, still the same number of MPI ranks per node, and still the same number of CPUs per task. This time here, you request the number of GPUs that you want on each node. So this 4 here means I want 4 GPU on each node, so you will end up with 8 GPUs. And the rest is identical. Here is an example, an excerpt from the log file when using GPUs with Gromacs. At the start of the log file, we'll see that the GPU support is enabled using CUDA. Then you will have a summary of the available hardware, and this time it should include the compatible GPUs for your MD. Then later, you will see how many GPUs were selected for the run. Important to mention, this is reported for a single host. So here we say 4 GPUs are running for Cedar 2546, the name of the compute node, but there's actually in a total of 8 compatible GPUs if you are running on 2 nodes here. But the number of GPUs per node is reported in the log file at this point. Then you will have, as usual, the number of MPI processes. Here I have 4 on each node, and the number of open MP threads per MPI process. So here everything looks fine. I have 32 cores in use on each node. Now in practice, how do you optimize Gromacs for using GPUs in your simulation? The best way to go is to start with a single GPU and the corresponding number of cores. So you just take the number, the total number of cores, and you divide it by the total number of GPUs, and this gives you the fraction of the node that you should be occupying with a single GPU. You do your tests, and then you can repeat increasing the number of GPUs. Use 1, 2, perhaps 3, 4 GPUs, and adjust the number of cores accordingly until you use all the GPUs on the node. Then, if you still see a good performance increase after you've used all the GPUs on the node, you can try using multiple nodes. However, my personal experience has been that GPU computing is really great when you use a single GPU. We are done with the bulk of the presentation, but I would like to present a few topics that are important for you to fully take advantage of Gromacs. The first is the tuning of the non-bonded interactions. I've already talked a lot about how non-bonded interactions are typically split into 2 parts. You have the van der Waals interactions and the short-range electrostatics that are computed in real space, and Gromacs will use these optimized SIMD routines or the GPU. And then you have the long-range electrostatics, which I said are computed in reciprocal space using the particle mesh Ewald method. And for that, Gromacs will use an optimized fast Fourier transform library. This means you will have a cutoff associated with short-range interactions and a grid spacing associated with the PME. and the balance between long-range and short-range interactions can be tuned. If you have longer cutoffs and a larger grid spacing, that means you will have more short-range interactions to compute. Conversely, if you use shorter cutoffs and a tighter grid spacing, it means you have more long-range work to do. Gromacs will automatically balance the short and the long-range interactions so that there is no waste of computational time. For that reason, it is no longer necessary or even useful to define the cutoffs or the grid spacing in your MDP file, and it is better not to define them at all. Another point is that Gromacs now uses verlet lists, and these don't need to be updated often. This is the NST_list parameter in your MDP file. Gromacs will ensure that the verlet lists are accurate anyway. And then a large NST list is especially important when working with GPUs, but it always makes sure that performance is good. And if the NST list is not appropriate, Gromacs will dynamically change it. What does this mean in practice? Simply, you can replace your non-bounded parameters in your MDP file by the following. You only have to define the periodic boundary conditions, specify that you do want to use verlet lists, have a high NST list, 50 is recommended, say that you want to use particle mesh Ewald for the electrostatics, you will use cutoff for the van der Waals, and you will shift them in a way that's appropriate for the verlet list. And that's it. You really don't need to specify the cutoffs explicitly or the grid spacing. The second minor topic I want to touch on is the integrator frequency. In our molecular systems, in MD simulations, usually the fastest motions are the vibrations between bonded heavy atoms and hydrogens. These bonds will vibrate at a, say, 10 femtosecond timescale, and so we require an integrator that's an order of magnitude tighter, about 1 femtosecond. Usually, however, we constrain the XH bonds in order to remove these vibrations. This makes it possible to use a 2 femtosecond integrator. Essentially, it makes your MD simulations twice as fast. This is pretty much always a good idea because we use rigid water models anyway. TIP3P or SPC, for instance, they were developed to have rigid bonds and even no angular motions. So it makes sense to also have rigid bonds, at least for the hydrogens, in your protein. It's even possible to increase your integrator frequency to 4 femtoseconds. However, when you do this, all your bonds will need to be rigid and there will be a trade-off between speed and accuracy. There are a variety of strategies to do this. In Ember, for proteins, we usually use virtual sites for hydrogens if we want to reach 4 femtoseconds. In Ember, mass repartitioning is used, where the mass, say on a carbon atom, will be split on the neighboring hydrogens to make these hydrogens bigger and therefore move slower. You also have the option of united atoms force fields. For instance, the Berger lipids do not include any hydrogen at all. There is one single bead that represents both the carbon atom and the bonded hydrogens. So the hydrogens not being there, the motions are not there, and you can increase the integrator to 4 femtoseconds. NameD uses a different approach with a RESPA integrator. This typically means that the bonded interactions will be computed every 1 femtosecond. The short-range non-bonded interactions will be computed only once every 2 femtoseconds, and the long-range electrostatics only once every 4 femtoseconds. So depending on which MD code you use, you have a variety of strategies at your disposal. I'm not going to go in details in any of them, but you should know that they exist and that if you want to make your simulations faster, you can take advantage of them. But there is a trade-off. In conclusion, always read your log files. Gromacs is very informative and will usually tell you if you make a mistake or if it detects that something is wrong with your system, the hardware, a software configuration, etc. I've said this already, but it bears repeating. Optimize every time you have a new system, unless that system is very similar to another system that you already optimized for. Another point is that sometimes multiple smaller trajectories are easier and faster to acquire than a longer one, than a single one. Well, they are always easier and faster to acquire, but sometimes it just makes more sense. What motions are you really interested in? If you want to see an event that happens on, say it takes 10 nanoseconds to take place, but it happens only infrequently, then it's probably a much better idea to have many smaller trajectories. But if you are interested in a motion that takes several hundreds of nanoseconds to happen, well, you know that your trajectories cannot be shorter than 100 nanoseconds. So it depends on what you are interested in, but usually more smaller trajectories make sense. And on that topic, a single call to MD-run can run multiple simulations at the same time on nearly arbitrary resources. And this includes, for instance, running several simulations at once on a single GPU. For that, you will need the multi-layer option, which you can have a look at in the documentation. Similarly, replica exchange and replica exchange with solute tempering can accelerate your sampling by using multiple replicas that exchange their coordinates instead of having one single longer simulation. These are more advanced techniques, but if you are short-pressed for more conformational sampling, you should know that they exist and that you can have a look at in the literature. Finally, always read the release notes when you change Gromacs version. Gromacs is a rather mature software, but despite that, it is still in active development. There is a lot going on. Performance increases pretty much every version. New features are added. Sometimes bugs are fixed. So it's important if you switch Gromacs version when you start a new project to read the notes and understand what has happened since the previous version that you were using. Now I'll leave you with a few pointers to documentation. First, on the Compute Canada website, we have a Gromacs page. The Gromacs documentation is extremely helpful and very well written. If you download the slides here, I left in annex an MDP file for recent Gromacs versions. I'll just jump to it briefly so you can see the output control, integrator settings, parameters for bonded and non-bonded interactions, simple temperature and pressure coupling. So have a look at that and compare with yours, especially for the non-bonded interactions, to make sure that you are running with optimized parameters. If you're interested in delving a bit deeper, the literature has many interesting papers. I would definitely recommend this one, Solving Software Challenges for Exascale, which is a little book that was published. And inside this book, there's a chapter dedicated to Gromacs, written by the Gromacs developers, and it gives you a very good idea of how Gromacs is structured internally and everything it can do. My only remark would be that this was written 5 years ago, and Gromacs has changed quite a bit since. So be careful, but it's still a very nice starting point. Another interesting paper, if you're looking to buy a workstation or even perhaps a local cluster and you're wondering what would be the best hardware to run Gromacs on, because I can't do everything on Compute Canada machines, well, then you could have a look at this paper in gComputeCan, which tells you how to optimize GPU nodes for Gromacs biomolecular simulations. It really tells you what you should buy so that you can get an inexpensive setup that will run extremely fast, so maximizing throughput. So thank you, and I hope that was helpful. I will see you in the Zoom session if you have any questions. And that's it. Thank you for listening.